I have completed the plans and now we'll take a look at all of the parts I need, although I'm still missing a couple of them. I still need to get the motor mount, and I just ordered the flathead screws that mounts the shredder to the transmission. Now for all of the parts, here is the chipper housing, shredder housing, rear mounting plate, chipper chute, chipper shredder rotor, DC motor and pulley, transmission mount, main bearing, support bearing, drive shaft, drive pulley, drive belts, some miscellaneous hardware, and 3/16 keys for the drive shaft. Now the first thing in this process is mounting the transmission to the rear plate of the shredder, and this will require careful locating and drilling 2 holes. Now back to the model to determine exactly where these holes need to be drilled, but first to see why I need those flathead screws. Here is the shredder with all the covers removed, showing the rotor. Making the rotor translucent, we can see I have 2 standard 5/8 hex screws as the mounting screws. This arrow shows one of the 2 chippers. Now turning the rotor, this edge here is the other chipper, and rotating just a little bit more, we can see that it cuts right through the head of the screw. Turning those 2 hex screws off and turning on the flathead screws, we can see that there's more than enough clearance for the chippers. And now it's time to mark up and draft the position of those 2 holes. Now it is time to draft, mark up, and drill holes for mounting the transmission bracket and bearing to the rear plate. First, opening up the assembly and then turning off all the housings and rotating around to see the screws. Now turning the screws off and then the mounting plate to enable measuring the distance between the 2 mounting holes on the bracket. Using the measure tool, I see that it is 5.825 and I write that down. Alternatively, you can use associative geometry in an assembly, but that is a landmine that could blow up in the future. Inventor does a horrible job in tracking links across geometry in an assembly. If the linked file moves or it is renamed, then there's practically no way to find out what the name was or where it was located so that it could be relinked. I will only use associative geometry as a temporary measure. Now turning the rear mounting plate back on and then changing it to transparent so I can see the transmission mounting bracket. Then opening the rear plate, starting a new sketch, then plotting 2 points close to where they should be, and now adding a dimension to the 5.825 measured earlier. Next I dimension 1/2 that distance to the center point and finally constrain the 2 points to each other on the horizontal axis and then to the center point. Finish the sketch and then put in the 2 holes. Back to the assembly and clear the override to the appearance, turning everything back on, then saving. Starting a new drawing and ignoring the scale prompt since it is not important, and just get to inserting the base model. Open the browser and select the file for the rear plate. Scaling it up using the corner grips to fit to the page and tick OK. Going to the Annotate menu and put in a couple of center points and add the dimension, ensuring it is what is supposed to be. Now let's get back out to the workbench. Now I've got it out on the workbench, ready to mark the points for the holes. The first step is creating a center line through that center hole. Using a straight edge tangent to 2 of the vertical holes, I mark a line. And now moving over to the other side, I do the exact same thing, marking a line tangent to the 2 outer holes. Now measuring the distance top and bottom to ensure those 2 lines are parallel. What I have is 2 7/8 inches top and bottom. Now finding the midpoint of the blinds top and bottom at 2 7/16. Then connecting the two marks, and now I have a center line right through the center of that hole. Now that I have the center line, it is time to mark the vertical pattern with the help of a 3D printed center point and a compass. I printed the hole pattern full size on a sheet, and I'll use that to set the compass. Putting the compass point on one center point of a circle and then adjusting the pencil lead till it meets the other. I find this more accurate than trying to actually measure the span. Once set, I make sure the pencil line is going through the center line of both holes in the pattern. But how do I find the center of the hole in the base plate? And here I have a little puck that I printed on my 3D printer that has a center divot in the middle of it. It fits right into the hole in the base plate and gives me a center point for the compass. And here's a close-up of the puck showing the center divot. I take it, drop it right into the middle of the hole, and now I'm ready to mark my pattern. Setting the compass in the center divot on my puck, and then marking through top and bottom lines. How to get a hole precisely where you want it? I use a center right precision marking tool. But too bad, these are obsolete. You can't get them anymore. It has a magnetic base that is dropped over the crossed lines on the layout. Now drop in the optical centering gauge and move the unit until the crosshairs line up on the layout. Let's see if I can get a view of this with the camera, but I don't think it's going to be easy. The optical centering gauge actually acts like a magnifier, looking through the crosshairs on the gauge, lining them up with the crosshairs on the layout. After a little manipulation with the camera, I think I got a good shot showing the center right optical gauge crosshairs as well as the layout. This was not easy to do looking through the camera viewfinder. And now that the magnetic base is centered on the crosshairs on the layout, we pull out the optical gauge and insert the precision center punch. A light tap with a hammer, and I have my center point marked, dead center on the crosshairs. Now it's time to drill some holes, and I will be using what is called a rotobroach or annular cutter. A common usage for these is drilling out spot welds, but they are perfect for any hole in sheet metal. The holes it makes is much cleaner than typical hole saws, and they are more accurate. I have the two center punch divots, which is what the annular cutter pilot mandrel uses to locate the hole. I'm using a 3/4 inch cutter, but it should have been 1 inch, but I don't have one that size. I will end up using the countersink to open up the hole. Because I am not drilling on a flat sheet, I will have to be careful or the pilot will be forced out of the center punch divots. I would rather be doing this on a drill press, but my drill press throat is not deep enough, so I will have to use a hand drill. This type of cutter requires lubrication. Failure to lubricate will quickly burn out the cutter. This is a machinist level lubricant used for cutting threads. It is very sticky and inhibits it from flying off. Now to reposition the camera to get a better look. Now we are set up to drill the first hole. Zooming in to get a better look at the center punch that will guide the mandrel for the cutter. As previously mentioned, because this sheet is not flat, the cutter is going to want to wander as I start the cut, so the first part of this is going to go slow. Spraying some lubricant into and onto the cutter, then place the point of the mandrel into the center punch. My drill was set to the low speed. I stopped here to show how it's cutting first on the high end of the plate. Too much pressure will cause the cutter to grab and pull it to my left. Once it starts cutting around the full diameter, then I can increase pressure. First hole is completed, and bringing the camera around for a close-up to see how nice and clean this hole is. Now to flip this thing around and drill the other hole.
No! No!
Now I have the backing plate and main bearing mounted to the transmission bracket. I am still missing the motor mounting bracket, so that is waiting for another day. I hope to have that in the coming week. Anyone that's been paying attention should notice that the orientation of the bearing has changed. It was at a 45-degree angle, but that interfered with the chute and I had to make a new transmission bracket. As I come around to the working end, you can see the rear support bearing for the drive shaft. And here is the rotor. And looking a little closer on the left side, you can get an idea of how the chipper works. I have this small branch in the chute to show how it engages the chipper blades. The chips from the branch are ejected through the slot in the rotor next to the blade. The vanes on the rotor actually function as a blower, ejecting the chips and shredded leaves out of the housing. The chipping blades need to be closer to the chute, but I am waiting for my new countersink to get the mounting bolts deeper into the housing. Back to the front end of the rotor to get a good look at the shredder blades. These are two sets of sharp blades. One is straight, the other is curved, to take care of leaves and twigs. Keep in mind that this thing is spinning around 4,000 RPM.